morning to all of you. We are discussing the theory of computation, that is deterministic finite automata. So in deterministic finite automata, we have seen the definition of DFA, right? Then the different types of or how we can construct the DFA, right? So what is the importance of the DFA in case of your theory of computation? And we have discussed various examples uh, on the DFA. Means so we have constructed DFA, that is deterministic finite automata, for various examples, right? So in today's lecture, we are going to discuss about NFA, that is nothing but your non-deterministic finite automata, right? So as we have discussed in the earlier unit or in the earlier lecture, that in DFA, that is nothing but deterministic, means there is only single transition. There is only single transition from uh, one input symbol to the next state. So one can say that yes, we can determine what exactly is the next state. For example, if there are two inputs A and B, so there is a single transition from state Q0 on input A, and there is a single transition on input B from state Q0 to the next state, and the next state, say for example Q1 and Q2, so next states are determined. So one can call it as a deterministic finite automata. But in case of non-deterministic finite automata, which we are going to discuss in today's lecture, so let us see here. Finite automata, it is called as NFA when there exist many paths from a specific input. There exist many paths from specific input symbol from current state to the next state, right? So hence it is called as the possibilistic machine. It is also called as the possibilistic machine. So see here, from state Q0 on input A, one transition goes to Q1 state, and another transition on same input, it goes to Q2 state. Getting this point? So one can say that on Q0, if I write here A, so there are two states are possible. That is nothing but your Q1 and Q2. So see here, again the transitions are shown here. See this. Q0 on A. Suppose if we see the transition function, if we see this transition function delta Q0A, right? So on input A, on the current state, it gives us two states, Q1 and Q2. Getting this point? So we cannot determine, see carefully, we cannot determine which exactly is the next state. So if you are at current state, if you, in the sense, if the machine is at current state is Q0, and the input applied is, for example, A, then the machine or automata can go to state Q1 or it can go to state Q2. Getting this point? So two new states are possible here. So two next states are possible, Q1 and Q2. That's why it is called as the non-deterministic. That is, you cannot determine what exactly the next state, because there are multiple paths exist. Multiple paths exist from current state on a single same input symbol. Same case with B. For example, delta Q0B. It goes to Q0 Q1. Q0, state Q0. Current state is, say, for example, Q0. On input B, self transition is there. This is one transition. And on the same input, on the B input, it goes to the next state Q1. So you have the cell Q0 and Q1 on input equal to B. So how many transitions are there on both inputs? Say if there are A transition, A input and B input. So on A input there are two transitions, and on B input there are two transitions. Total 4 transitions are there. Total 4 transitions are made from the current state Q0, right? So we can call, so such type of automata is called as your non-deterministic finite automata. It is called as the NFA. One cannot be determined what exactly is the next state. So there can be multiple final states. You can find here there can be a multiple number of final states are available, right? So see here, and it is also possible that in NFA, what we are doing, so we are taking the transitions on all input symbol. Remember the difference, or listen it carefully. In NFA, while we are constructing DFA, what we are doing, we are considering the transitions on all input symbols. But it is not the case in case of NFA. there may be some input, there may not be transitions on some input symbol. For example, Q1, there is only transition on input A, but Q1 on B, you can have 5 transitions. I mean, there is no transition on input B on from state Q1. Getting this point? So I can write here Q1 on A, you can have Q1, the state itself, but Q1 on B, there is no transition. It is called as a empty. That is nothing but the phi, right? Q2. So Q2 on A, that is equal to phi, and Q2 on B is equal to phi, because there is no transition from state Q2 on either input, either A or B. So that's why you can mark it as a phi. So this is possible in our NFA, but in case of our DFA, you have to exclusively mention the transition on each input symbol. If it is the case of DFA, you must mention what exactly the next state on input A to the state Q2, and what exactly the next state for on input B for the current state Q2. Getting this point? So that is another difference. So first difference is that yes, there are multiple paths are available, or there are multiple transitions on the current input symbol, and the second difference is that there may not be the all input. There may not be transitions on all input from the current state, right? Next point is that this NFA is used in the theory of computation because they are more flexible and easier to use than DFA. Means they are not, one can say that they are more flexible. Why? Because you can have multiple paths are available. Means just like your parallel processing, you can have, means on Q0 you can go to Q1, as well as on Q0 on A you can go to Q2. Means there are multiple options are available, that gives more flexibility to your NFA, and they are easier as compared to DFA. Means DFA, there are very rigid boundaries, or there are strict constraints are available in case of your DFA, but in case of NFA, there are no such constraints, there are no rigid constraints available. That's why it is called as they are very easier as compared to your DFA. Getting this point? Okay. The next point. In NFA, the transition function must specify all possible states that the machine may enter from a given input symbol. See here, the transition function, meaning is that the transition function must be written for all the possible states given in the transition diagram. See here, the three diagrams are given, 3 transition diagrams are there. So you have to write down all the possible transition functions. So these are the transition diagrams. So for the transition diagram, the transition function delta Q0A go to Q1 state, right? The second transition function diagram is Q0 on A go to Q1, Q0 on same input A go to Q2, Q0 on same input go to Q3, right? Because it is NFA, it is nothing but your NFA, and so that's why you have to write down the transition function. This is the transition function. Q0 on B go to Q1, Q2, Q3. So this is the transition function for this particular diagram. And for this Q0, the transition function is written as delta Q0A, that is equal to phi. That is equal to phi, means it does not go to any other state. It is the input after applying this A input, the state, there is no self transition as well as there is no other transitions available. That's why it is marked as a phi, right? NFA can be in several states at any time. So these are the characteristics of NFA. So first characteristic is nothing but NFA can be in several states at any time. Means yes, it can be in a multiple state, but DFA at one time it must present in one state. But NFA at one point of time it can have in a multiple states can be possible. Every NFA can be converted into equivalent DFA. The important point. So NFA is given. Say for example, here I write here NFA. So this NFA you need to convert into DFA, right? So if there is a way, there is a method to convert. Suppose a given NFA is there, you have to convert this NFA into deterministic finite automata, and this is possible. This is possible. There are standard method. Due to non-determinism, see here, due to non-determinism, NFA takes more time to recognize the string, because it can have multiple states. NFA at a point of time, it can be in a multiple number of states. That's why it takes more time. Suppose you have to recognize the string, for example, double A double B. So if you design a DFA for this, so DFA will recognize, or DFA gives you the answer very faster as compared to your NFA, because NFA may take multiple NFA have multiple number of transitions on same input symbol. That's why it takes longer time as compared to DFA. And NFA can be designed with a fewer states as compared to the DFA. This is also possible. You can design NFA with fewer states as compared to DFA. Means, for example, if you want to design a DFA, or if you want to design a NFA for a particular language, the same DFA can consist more number of states as compared to its NFA counterparts. Getting this point? So these are the few characteristics of your NFA. That is nothing but your non-deterministic finite automata. Let us go to the next slide. So definition of NFA. The definition of NFA, as already we have seen the definition of DFA, the same definition is here. Only one difference in the transition function. Only one difference in the transition function. See here. So Q. So as you know that Q, capital Q, is nothing but your finite set of states, that is Q0, Q1, Q2, Q3, up to dot dot dot. Then sigma, finite set of, we can say finite set of input alphabet. You can have 0, or you can have 0, 1, you can have A, B. Any input symbols you can take here. Initial state is Q0, F is always marked as a final state, and delta is nothing but your transition function. Delta is the transition function, and see here what is the difference. So Q into sigma gives you 2 raised to Q. This is the only difference, and this difference you must always, this particular difference you must always remember. This is your NFA definition, or this is your NFA transition function, right? So in case of DFA also, this thing, all the things are similar, but only a delta you can have. In case of a DFA, delta you can write like this. What is the function? What is the transition function for DFA? Delta Q into sigma gives you Q, right? In case of your DFA, means Q is nothing but your current state. This sigma is nothing but your input symbol. This gives you the next state, right? So same case here also, you have the current state, you have the input symbol, and here you are getting next state. But here 2 raised to Q next states you are getting, because there are multiple transitions. These are multiple transitions on same input symbol. Meaning 2 raised to Q. Say for example, if you have how many? If you have Q0 and Q1, if these are the 2 states are available, then how many 2 raised to Q? 2 raised to Q means 2 raised to 2 means how many new states, or how many states you can have possible? There can have 4 multiple number of states are available. Getting this point or not? For example, if the Q is, say for example, Q0, Q1 and Q2, how many states? This is equal to 3. This is equal to 3. So how many next states are possible in case of your new states are possible in case of this particular NFA? So it becomes 2 raised to 3. That is equal to 2 raised to 3 is equal to 8. Right? So this is the difference. This is the difference. But in case of your DFA, you have 2 states Q0, Q1. So Q0, Q1 here, input state, and multiplied by input, you at the at this end you get here Q0, Q1 only, because it is a deterministic finite automata. But in case of your non-deterministic, this particular next state, or one can say new state, they are in the power of 2. They are in the power of 2. Getting this point? So this is the difference, and remember this equation. So you have to remember the equation for DFA and NFA. What is the difference between the transition function? So for the DFA, so sorry, for the DFA, this is the equation, and for NFA, this is the equation. Getting this point? Okay. Let us go to the next slide. Difference between NFA and DFA. Difference between NFA and DFA. See here. The DFA is deterministic finite automata, and whereas NFA is non-deterministic finite automata. As you know that DFA is the deterministic, whereas NFA is the non-deterministic finite automata. The first difference. The second one, in DFA, for a given state, on a given input, we can reach to a unique and deterministic state. Only one transition is possible. The meaning of the statement is like only one transition from, say for example, Q0 on A, it will go to definitely Q1 state. Getting this point? But on the other hand, in NFA, we may lead to more than one states for a given input symbol. For example, Q0 on A go to Q1, whereas Q0 on A go to self loop also. This can also be possible in case of a NFA. The DFA is a subset of NFA, so you can have DFA is a subset of, suppose if NFA, if I write like this, so this is a symbol of subset, so I can write like this. So DFA is nothing but the subset of NFA. We need to convert the NFA to DFA in the design of compiler. So probably in the next semester, software system programming or system software subject, you have the lexical analyzer, you have the design of the compilers and all the system software. So in that particular case, these concepts of theory of computation, DFA, NFA, these are very much useful because these are the basic. They are the basic concept and they are used in this particular compiler design, right? Okay, so next point, the significance of NFA or the significance or the importance of NFA. Let us summarize the significance of NFA. Computers are basically deterministic machines. That means on given certain input, we get certain output. In similar manner, DFA are the machines in which we get some predictable state on certain input symbol. Predictable state means, yes, we can predict after Q0 giving input A, it will go to only Q1 or Q2 state. The predictable states is possible in case of DFA. But constructing such a DFA is very difficult. Hence, there should be a way to build easy to construct a machine. In such a case, we construct a non-deterministic machine, which is called as a NFA or NDFA. It is also called as a non-deterministic finite automata or NFA or NDFA. This NFA then can be easily converted to DFA. This efficient mechanism is majorly used in compilers. So there are some problems, or there are some compiler issues, or there are some designs that cannot be directly designed to DFA. Means for a particular problem, you cannot directly go for DFA because constructing the DFA is a tedious part, or it is it involves somewhat complications. So what you have to do here, you have to first construct a NFA. Means NFA means what? You have your you can have your free hand available. Means on a same input symbol, you can have multiple transitions possible. Once you can construct a NFA, or once you have developed a NFA, then this NFA you can convert into the required deterministic finite automata or the DFA. Getting this point? Okay. Okay, see here examples on NFA. So we'll see some examples. Few examples are there on non-deterministic finite automata. Already we have seen examples on deterministic finite automata. So this is the first example. Design NFA over input alphabet 0, 1, 0, 1 to accept the string containing substring 0, 1, 0, 1. The method is very similar as that of your DFA. Already that we have discussed. So 0, 1, 0, 1, 0, 1, 0, 1. And the rest of the transitions, so there is a transition mark only for Q0 and Q4. 0, 1 you can have here, and 0, 1 on the self loop on Q4, and 0, 1 on the self loop on Q0 itself. For rest of the Q1, Q2, Q3, no need to mark explicit transition, as just like your DFA. In case of DFA, what we have to do here, we have to mark, suppose 0 is here, or 0 transition we have to mark here. But in case of NFA, no need to mark the transitions on all input symbols, right? So see here the transition table. So Q0 on 0, it will go to Q0, Q1, yes, Q0 and Q1 on 0 input symbol. At the same time, Q0 on 1 input symbol, it will go to Q0. So it will go to Q0 only. Q1 on 0, it is phi. Q1 on 0, because there is no transition on 0 input symbol from state Q0. That's why it is marked as a phi. Q1 on 1 input, it will go to Q2 state. Q2 on input 0, it will go to Q3 state, and Q2 on input 1, it is marked as a phi here. It is marked as a phi. No transitions is available. So Q3 on 0, no transition, that why I mark as a phi. Q3 on 1, it is marked as a Q4. Q4, which is the final state. Q4 on 0 and 1, both are lead to Q4 states, right? So this is the way. So this is the way we have drawn the transition diagram, and this is nothing but your transition table for this particular example. Let us see the next example. Design NFA for given transition table. Now the transition table is given to you, very simple. So Q0 on 0 go to Q0 Q1, Q0 on 1 go to Q0 Q2, Q1 on 0 input go to Q3 state, Q1 on 1 there is a no transition, that's why it is marked as a phi. Q2 on 0 input go to Q2 Q3, and Q2 on input 1 go to Q3, whereas Q3 on 0 go to Q3 and Q3 on 1 go to Q3. Very simple, you have to draw the NFA. See how the NFA is drawn here for the transition table. 4 states Q0, Q1, Q2, Q3, and all the transitions, whatever maybe the transitions are here, all these transitions are now converted into the transition diagram. It is called as your NFA. Right? Very simple. What you have to do here, you have to just practice it. You have to take your paper pencil and just start drawing this NFA step by step, how to draw the NFA or DFA. You just practice it. Then it is very simple. There is no any one can say mathematics or no any difficulties involved in this particular drawing this automata. Only practice is required, and you have to think logically. Next examples on NFA. Design NFA to accept the strings that end with double A. Similar to your DFA, the example is given here. Design an NFA, non-deterministic finite automata, to accept the strings that ends with double A over input A comma B. Okay, so just like our similar Q1 on A go to, sorry, Q0 on A go to Q1 and Q1 on A go to Q2 state. Very simple. And mark this Q2 as a final state. I mark it as a final state. Okay, and so Q0 on A, I can have here A, so multiple transitions are possible, as well as I can mark B here, right? Then Q1, no transitions I have marked here, but for Q2 on A, I can mark here A because I need here double A. At the end, there must be double A, and B I can mark here for Q2 on B go to Q0 states. Very simple. Already we have discussed. There is no difference at all in case of our NFA DFA, but only the thing is that yes, we can mark multiple transitions just like here. We can mark the multiple transitions. Example number 4, design a NFA for a binary number where the first and the last number is same. Binary number, we take a binary number, for example, 0, 1, 0, 1, 1, 1, 0, 1, 0. So first number and the last number must be the same. So we have to construct a NFA machine or NFA automata. See here. So this one can call it as if this is nothing but your first number and the last number. Either it may be 0 or the first number may be 1 and the last number may be 1. Getting this point where the first and last number is same, meaning is that there may be two, because it is a binary. Because it is a binary, so only two cases are possible. Either the first number and the last number is 0, or either first number and last number is 1. So this second case is possible. Right, so that's why 0, 0, first number 0, then it will go to Q1. I can have multiple transitions, 0, 1 on Q1 itself, and Q3 it will 0 on 0 go to Q3. From 1 it go to Q2, Q2 I can have multiple transitions on 0, 1, and Q2 on 1 go to Q4. Very simple. There is no any difficulty involved while drawing this NFA, right? Okay, let us go to the next one. Yes, this is the next topic, that is NFA with epsilon moves. It's a very important topic. Now, you know the concept of NFA. NFA, what is the significance of NFA or application of NFA? What exactly is the difference between NFA and DFA, right? And we have also seen how to draw the non-deterministic finite automata. Some examples we have seen here. Now we'll see the topic, that is epsilon moves. What exactly is the epsilon moves that we are going to see here? So look at the diagram. Epsilon transitions, right? So epsilon transitions means this is your epsilon transitions, means it is nothing but no input symbol, means there is a transition without inputs, right? So read this. So epsilon transitions on NFA are given in order to move from one state to another state without having any input symbol. Without having any input symbol means there is a transition. There is a transition from current state to the next state without input. That is called as a epsilon transition. That is called as epsilon transition. So, for example, Q0 on 0 go to Q0. Okay. Now Q0 on 0 it will go to Q1, and Q0 on epsilon it again go to Q1. See here. So this epsilon is called as the epsilon transition. So I can have Q0 on epsilon, it will again go to Q1 state, right? and q0 on 0 it will go to 2 state, that is nothing but your q0 q1. So if I write the transition functions, so I can have q0 on 0 it will go to q0 q1, whereas q0 on epsilon it will go to q1 state only, right? So epsilon transition means what? There is no input, means epsilon means it is not 0, it is not 1, it is empty transition, means. So what is the meaning of this? Meaning is that your machine or your automata, it may change the state from current state to the next state without being applied any input. It is called as epsilon transition or empty transition. This in this NFA with epsilon, q0 is the start state. With input 0, one can either be in a q0 or q1 as shown in the figure. If we get at the start a symbol 1, then with move we can change state from q0 to q1. On the other hand, from state q0 on input 1 we can reach to q2 state. So here this is also possible. q0 on one input we go to q2 state. Epsilon stands for a null symbol. Epsilon stands for null symbol. A epsilon transition allows transitions on or no input. Transitions on or no input. That means this implies that a machine can make a move without having any input applied. So remember this point. Without having any input, the machine can change the current state to the next state, and this is called as the epsilon transition or E transitions. Empty null symbol. This epsilon is nothing but your null symbol. Remember this one. Right, and this epsilon transition has got more weightage or more importance while drawing this NFA, because NFA with epsilon has got more power as compared to the simple NFA. Getting this point? Just we'll go to the next slide. NFA with epsilon or ENFA, it is also called as the ENFA. Now the definition. Again, it has a definition. Just like your NFA, similar to your NFA definition, the definition consists of capital Q. Capital Q is nothing but the finite set of states. Then sigma is nothing but your finite set of input alphabet. Then Q is nothing but initial state, and F is nothing but your final state. All the thing is same. The difference is here in the transition function. Q into sigma, Q into input, it gives you Q into sigma gives you 2 raised to q. This is the case of your NFA. This is the case in case of your NFA, and this is the case of your ENFA. NFA with epsilon. This is called as epsilon NFA, epsilon dash NFA. It is called as ENFA. And what is the difference? So union epsilon. See here, union epsilon means along with input. So input may be 0, 1. Along with the input 0, you have to consider this epsilon transition. Suppose there is only one q0 state, so I have to consider q0 on 0. I have to consider q0 on 1. Along with that, I have to also consider q0 on epsilon transition. What will be the next state? Getting this point? What is the significance of this particular transition function? So here it is the explanation. Means for each state with the regular inputs, whether regular inputs means either it is 0 or 1, or it can be a comma b. Along with these inputs, what other transitions on this particular epsilon transitions, that also we have to consider. That is nothing but like this q0 comma epsilon, and what is the next state or the new state. Getting this point? So this is the difference. So this is the in case of your simple NFA without epsilon transition, and this is nothing but your with epsilon transition. This is with epsilon transition. Getting this point? Significance of NFA with epsilon transition or ENFA. We'll see the importance, why this ENFA concept is introduced in the theory of computation. Let us see point one by one. The first point is, suppose we have to construct a DFA for a language that accepts all strings consisting of any number of zeros followed by any number of 1. For example, any number of zeros followed by any number of 1. Suppose we have to construct a DFA for such a strings, but it is very difficult to construct such a DFA directly for this language because it involves multiple number of states and the transitions are there. So it is very difficult task, or it is a very critical task to design a DFA for such a critical problem. So what we have to construct here, what we have to do here, we have to construct a NFA with epsilon moves. We have to construct the NFA with epsilon moves. Then this NFA can be converted to DFA. As epsilon is an empty string, the epsilon transitions are used simply to change one state to other state. So this is the important point. Epsilon, it is nothing but the empty string. There is no input associated with the transition. That's why. So when the machine or when the automata want to change the one state on it, want to go to other state, you have to use the transition. That's why it is given here, one state to other state. Q0 is there and there is no input transition from Q0 to Q4. You just make it as epsilon, and from epsilon just automata changes the current state Q0 to Q4 state, and from Q4 there can be transition possible on the given input symbol. Getting this point? So sometime to reach to final state, we do not get proper state from start state. In such case, we simply want to reach to certain state which leads to final state. So yes, if there are multiple states, if there are 10 or 15 number of states, and there is very difficult to reach to the final state. So what is to be done in this case? We introduce epsilon transition, means just change the current state to the next state without giving any sort of input. And in that particular case, it is very easy to reach to the final state. So such a transition to that specific state should be without any input symbol. Without any input symbol means it is nothing but a epsilon transition. So hence we require some epsilon moves by which a proper state can be obtained for reaching to the final state, right? Thus epsilon moves plays an important role in NFA. That's this is the importance of your ENFA. This is the importance of your ENFA. Getting this point? So important is that if it is very difficult, so there are the two main point is to be remember. It is very difficult to construct DFA for some critical problem. In that particular case, you need to design a NFA with epsilon moves, right? This is the first case, and second case is that there may be the possibility that there are several number of states, and it is very difficult to reach to the final state. So with the help of your epsilon transition, with the help of epsilon move, you can able to reach to the final state within limited amount of number of states, because for epsilon transition you don't require any kind of input. Getting this point? That's why this ENFA plays a significant role in your designing your NFA, right? The next point is nothing but your epsilon closure. Epsilon closure. See here. So E transition concept is clear to you. Now E closure. What is the E closure? Let us see. E closure means what? Epsilon closure or the E closure of any state, epsilon closure or the E closure of a state, it is defined as for state Qi is the set of states including Qi, including the current that particular state, where Qi can reach by any number of epsilon moves. Getting this point? Of a given NFA means from given state with epsilon transition, how many next states are possible? That means it is the set of states with distance 0 from the state Q. That is called as your E closure, E closure of state Q. So E closure of a state Qi includes Qi itself, the first point. Then set of states reachable from Qi on epsilon moves, and the set of states reachable from existing states in E closure using the epsilon moves. In a very simple word or in a simple way, I can define the E closure like this. Suppose, let us see example. Q0, there is a transition on A, it will self transition. Q0 on epsilon transition go to Q1. Q1 on B, self loop. Q1 on epsilon go to Q2, and Q2 on self loop is C. Getting the self loop on input C. Now if I want to define, the E closure of Q0, epsilon closure of Q0. So definition says that, see your definition, the E closure of a particular state include the self state or the state itself, the first point, and epsilon reachable states. This is very important. Or the states which can be reached on epsilon transitions. The E closure, if I want to find out the epsilon closure of state Q0, so I write here E closure of Q0, the state itself, And from epsilon, all other epsilon transitions. So Q0 on epsilon go to Q1, and Q1 on epsilon go to Q2. Means Q0 can reach to Q0, can reach to Q1, and it can reach to Q2 state. Getting this point or not? Meaning is that the epsilon closure tells you that the particular state reaches to how many different states on the epsilon transitions, on this particular epsilon transitions or epsilon moves, right? So E closure of Q1, So E closure of Q1 is the state itself. So first write down the state itself. The rule is that, so remember this rule to find out the E closure of any state. So this is the rule. So first write down the rule itself, because the state can move to itself. That's why it is called as a, that's why it is marked as a Q1 here, and Q1 on epsilon it go to Q2 state, right? And Q2 on epsilon it does not have any transition. That's why it is only written here Q2. So epsilon closure or E closure of a particular state is nothing but the set of states. It is nothing but the set of states with the distance 0 from the state Q. And so these are the three things you have to consider while finding out the E closure of particular state. E closure of state Qi include the state itself. This is the first point. The state reachable directly reachable from Qi, the E moves, and the states reachable from existing state. These are the indirect states. So from Q0, for example, on Q0, this is the first, this is nothing but the self state. Now Q0 directly goes to Q1 on epsilon, right? And Q0 it indirectly go to Q2 on this epsilon, because Q0 on epsilon go to Q1. Definitely from Q1 there is a epsilon transition to Q2 from Q1. That's why it is a indirect states from Q0. That's why this is called as the E closure for state Q0. This is called as the E closure for state Q0. The same is for Q1 and same is for Q2, right? Let us see. E closure of any state is denoted by and written as like this. And one example, so E closure of any state, so delta cap, so it is written like this. If you have to write in your notebook, you have to write like this. So in this machine, this is not possible, so that's why the symbol comes here. But in your notebook, you can write like this. So delta Q and epsilon, that is nothing but your E closure of state Q. So delta cap, you have to write like this: delta cap Q0 epsilon, it is nothing but your E closure. So here I am writing with my hand and pen E closure of Q0. So delta cap, remember this symbol, delta cap, it is not a transition, but it is nothing but the E closure. Remember, only simple delta represents the transition function. But if it is a delta cap, this delta cap is nothing but your E closure. It gives you E closure, right? Okay, so the NFI with E closure is given to you, and here just write down all the possible states, or all the one can say epsilon closure for all the states here. So if I write here delta cap Q0 epsilon, means that is nothing but, this is nothing but my E closure or epsilon closure of state Q0. Remember this point, E closure of Q0. So E closure of Q0, the definition says that it includes the state itself, that is Q0 itself. Okay, yes, it is included, and the direct state from the epsilon transition. So from Q0 directly it go to Q2. That's why Q0 to Q1. That's why Q1 is marked here, and Q0 on directly epsilon go to Q7. That's why Q7 is marked here. Right now indirect states. Which are the indirect states? From Q1. Q0 on epsilon go to Q1, and Q1 on epsilon is go to Q2. That's why Q2 is marked here, and Q1 on epsilon is go to Q4. Here is again epsilon transition. That's why Q4 is marked here. But from Q2 it does not go to Q3, because this is the zero transition. There is a transition from zero input. And on Q4, see, it is very important. On Q4 you cannot go to Q5 on epsilon, because there is a transition on input 1. There is a transition Q4. So this is like this: Q4 1, it go to Q5 state, but Q4 epsilon, this transition is not available here. So that's why you have to stuck up here. So q1 epsilon q4, q1 epsilon q2, but you cannot go to q3 and q5 states. That's why this is called as the E closure of Q0 state, includes Q0, Q1, Q2, Q4, Q7, all the states that are possible from epsilon transition from the current state, right? Just clear this. So same way, delta cap Q1 epsilon, delta cap Q1 epsilon. So we have to see Q1, the state itself Q1. So on epsilon it go to Q2, that's why I mark as a Q2, and epsilon it go to Q4. So all the direct transitions are available. There is no indirect transition. No indirect transitions are possible for Q1 states. That's why only 3 states, that is called as the E closure. Remember this point, E closure of Q1. It is also written as delta cap of Q1 epsilon, right? The same way for all the states, E closures are written here. Q2 epsilon, it will go to only Q2 because there is no transition on input epsilon, because there is only one transition on 0, it will go to Q3. Epsilon, no transition is available, that's why it is marked as Q2 only. Q3 epsilon, yes, Q3 epsilon here on Q3 and epsilon it go to Q6. So first write down Q3 state itself, then it will go to Q6, Q6 go to Q7, that's why Q7 is marked here. Now Q6 again go to Q1, so Q1 is marked here, and Q1 go to Q2 and Q4, that's why Q2 and Q4 are marked here. That is nothing but your epsilon closure of your Q3 state. Means these are, so Q3, Q6, Q7, these are the direct transitions from epsilon transitions, whereas Q1, Q2, Q4, these are the indirect. One can say, the transitions on epsilon, right? The same way, Q4 epsilon, only Q4, there is no epsilon transition on state Q4. Then Q5 epsilon, yes, see here, Q5 and epsilon same as your Q3. It will go to Q5 to Q6, Q6 to Q7, then Q6 go again Q1, Q2 and Q4, right? Q6 go to Q1, Q2, Q4, and Q7 is also there. And finally, Q7 epsilon goes to Q7 only. There is no transition on epsilon input, on epsilon symbol from the state Q7, right? So these are called as the E closure. Remember this, how to find out the E closure. Epsilon closure of the current state, right? It is marked as a delta. Always remember this thing, because this thing we require in the next point. Remember this, how to find out the E closure of the state. It is very important. So just go through it again and again. So how to find out the E closure of state Q0, right? So take the state itself, the direct epsilon state and indirect epsilon state, that we have to consider here, because this we require in the next topic, right? Okay, so what we have learned in this particular session, that non-deterministic finite automata, NFA, the examples of NFA, the definition of NFA, significance of non-deterministic finite automata, what exactly is the difference between your DFA and NFA, that already we have discussed, and NFA with epsilon, the very important topic, the epsilon transitions, or one can call it as nothing but the transitions where the no input is involved, empty string is there, and still the automata changes the state from current state to the next state on the NFA with epsilon modes. The course outcome attainment, to construct the finite state machines to solve the problems in computing, the reference book, as already I mentioned that the books you have to refer, the reference books. Okay, so let us stop here for the today's session. The timing of the next lecture I will display